We now consider a new application of integrals, so not a technique, but a reason why we might want to calculate them in the first place. We've seen the idea of integrals representing areas or accumulations. Here we're going to see how they connect to the idea of an average in a more generic case than simply the average of two numbers or the average of a fixed number of values. For example here, imagine we have a graph where we're measuring carbon dioxide in the air in a greenhouse. And we see that it goes up and then sort of stays at this low level, and then on the second half of the week it's closer to this upper level. Well, what might we expect to say as the average there? Well, I don't know, 400 maybe? Maybe that's sort of the average level. It's certainly not going to be 450 because there's too much time spent with low levels. It's certainly not going to be down here at 350. So somewhere around 400. So around 400. And what would the units of that be? Well, if we say on average the carbon dioxide level is 400, it would be in exactly the same units as the function itself. In this case here, as CO2 as a function of time. Okay. That gives us some ideas as what we're looking for when we talk about an average value, and we're going to use this graphical perspective on it to help us narrow down how to actually compute the exact value of this average. All right, let's sketch the nice quadratic. Rather than go into the application area and as a hard example to start with, let's start with our familiar y equals x squared graph. There we go. So the y equals x squared graph looks like this. There we go. And estimate the average value on this interval. Well, again, it starts at 4, so 4 up here is the height, and we got 1 here when we're down at 1 and -1. And we're doing it on the whole interval from -2 to 2, so that's what we've got. Well, I don't know. It's higher than 1, that's for sure. Like maybe a good height on average would be something like between 1 and 2, 1.5 maybe, something like that. Well, it's hard to see, so let's explore this a bit further. What would make the average the average? I think if we consider a little Goldilocks scenario here, let's choose a too high example. And we'll choose a too low average. And again, remembering the average is a y value. So what would be just right? Well, what makes this value too high? One way to look at this is when you think about averages, you think about equal distance between all the points back to the average value. Here we have a curve, so we have an infinite number of values actually. And we'd say that, well, some of the values are too high, they're above the average, but most of the values over longer intervals are below the average. Well, that seems unbalanced somehow. When we look at the average here and say, well, could that be the average? I don't think so, because we seem to have, again, an imbalance where more of the graph is above this line than there is graph below it. Oh, actually, that's a good idea. Maybe not the graph, but the areas. So this has more area above the average line than below. And somehow that seems out of balance. Here we have the opposite scenario. There's more area below the average line. And then above. Here we just have a little bit above, way more below. So this doesn't make sense as an average. What would be the sweet spot? Well, maybe a little bit above that, like maybe here. And it might be the region. That's even a little bit too low still, I think. Let's go a bit higher. Let's go up to 1.5 and see what it looks like. Where this area and this area, the area above the average y value is equal to the area below. Okay. Now, how can we compute that? Well, that's not too bad, actually. If we think of what we've just done here, we've moved a scale. We could have the area minus the average, sorry, the function minus the average. When we add that up with little units of delta x, so if the function's above, we get positive. When the function's below, we automatically get negatives. In this case here, we're talking the general case, so from a to b. If we had the function being above the graph times little units of delta x, canceling perfectly with when the function is below the average, so we get negative values here, times little units of delta x. If that all cancels out and gets 0, then a would be our average value. Let's see how that plays out with our x squared example. So if we are looking at the interval from -2 to 2 of x squared minus a, and we want that to be 0, so this is our equal area condition. Equal area above and below y equals a. Then we're going to solve for a. What is that average value that's magical? Let's go hunting for it. If we, oops, I forgot a dx here. We have to have, this is a sum, x squared minus a times little units of delta x. When it comes to the integration, though, the a is just a constant. We don't know what it is, but it doesn't change. So we can integrate this and get x cubed over 3 minus ax between -2 and 2 is equal to 0. And what does that give us? Well, it gives us -8 over 3. Whoops, flip the limits of integration. Oh. Positive 8 over 3 minus a times 2 minus the lower limit of integration. This is -8/3 minus -2 times a must equal 0. What does that give us as we combine them? We have -a times 2 minus minus minus. That's still a negative, so we end up with -4a's. And we have an 8/3 plus 8/3, that's 16/3 equals 0. Our a, then we bring it to the other side, that's 4a equals 16/3. And so the average y of x squared on the interval -2 to 2 is going to equal this a, and that's 16/3 divided by 4, or simply 4/3. We're going to flip back for 1 second and see 4/3 just a little bit above 1, or between 1 and 1/2, and so actually the real average would be a little bit below that. And again, that would give us exactly the same area in this bulge down here compared to the area over here. In fact, we can almost see this is a little bit too big compared to the area sketched out here. Going down a bit would balance that area out above and below the graph. So the average value of f of x equals x squared on this interval would be the height y equals 4/3.